Good morning, SUPA world. How is everybody? We're going to start chapter 11 today, and we're going to be dealing with a bunch of stuff on intermolecular forces. Actually, some of the stuff that we're going to quick talk about today we've already gone through. But that's okay. So, first thing I kind of want to start with, right, are our three phases. So we have solids, liquids, and gases, right? And we've spent a bunch of time talking about gases, and we basically said in the kinetic molecular theory that there are no attractive forces between these particles in a gas. Before, when we were talking about solids and liquids, we said that these particles are held together by these forces between the molecules called intermolecular forces. And those are the things that we're going to start by talking about. All right, so let's just quick go back through and summarize some things about solids, liquids, and gases. All right, and I want to do that using a heating cooling curve. Okay, so our solid is here, our liquid is here, our gas is here. All right, if we're going up the graph, it's heating. Okay, so energy is being absorbed. This is a cooling curve if we come backwards. So if we're going up, it's melting, fusion, down, freezing, solidifying, crystallizing. Okay, then we have a liquid. Okay, so this would be vaporization or boiling, and then coming down would be condensation. Okay, so these are all things that we've talked about. Calculations of heat, or Q. Okay, so when we're in phase, so here, and here, we would use Q equals mc delta T, mass times the specific heat times our temperature change. Here we would use Q equals mhf, Q times the mass and times the diffusion. In here we would use Q equals mhv. So we've talked about all of those. Right, so let's just quick summarize solids. And we've already done this. Right, so like in the picture here, our solid, right, we have that nice strict geometric pattern. The particles are close together. The particles just can sit here and vibrate, okay, and they have a definite shape and a definite volume. Right, so they have a strict geometric pattern. The particles just vibrate. Molecules are close together. They have a definite volume and shape. Now, as we heat this solid up, the particles vibrate faster and faster and faster, and eventually they start to overcome some of the intermolecular forces. Now, not completely, all right? They don't overcome them completely, but they allow these particles to start to spin. And once they can start to spin, they can slide by each other, and this geometric pattern breaks down. Now, the particles are still pretty close together. Not quite as close together as that, but they're pretty close together, right? And these still have strong intermolecular forces because it holds all those particles clumped together. So let's write some things about liquids. And I think this is all review. Right, so we know that the particles vibrate and rotate. They're still close together. They can slide by each other. And that breaks the geometric pattern. And they have no, take the shape of their container. And they have a definite volume. Okay, so no definite shape, but they have a definite volume. All right. Now, if we start heating this liquid up, the particles will vibrate, rotate faster and faster and faster and faster, and eventually they'll have enough kinetic energy where they can break away from these intermolecular forces. So if there is no intermolecular force here, if it has enough energy to break it, this guy can go up into here, and we start to boil this off. Okay. So we know our gases vibrate, rotate, and translate. They have no definite shape or volume. And they expand to fill their container. All right, so if we come back down here, back up here to our heating cooling curve, remember we can figure out melting and boiling point. So this substance melts and freezes at this temperature, so we could come back here. This would be its melting point or freezing point. Remember, they're the same, right? If we come back here, this would be our boiling point or our condensation point. Okay. Remember, we're changing kinetic energy here on the slants. Okay, and we know that because the temperature is changing. Temperature does not change during phase change. Okay, so our kinetic energy stays the same. This is where our potential energy is changing. I think that's pretty much it from here. There's a couple little things that I want to talk about, okay, that are special. And it's called superheating and supercooling. So superheating is when the temperature of a liquid exceeds or is higher than the normal boiling point. Supercooling is the temperature of a liquid is below its normal freezing point. And when a liquid does this, when a liquid is in one of these states, it's called a metastable state. Oops, state. Now let's talk about these for a minute. So you can actually see these happen. Sorry, I'm drinking my coffee this morning. Did you know that you are not supposed to heat water up in your microwave oven? And the reason why is it will often superheat, which means, so let's say that we have a glass of water. We have our glass of water, and we put it in the microwave, and we heat it up. It will often, this liquid will often superheat, which means it could have a temperature of 110 degrees. Now, remember, water normally boils at 100 degrees. Now, why does this happen? Well, it has to do with surface tension of liquids. And we're going to talk about that, in this unit. So the surface tension of water is very high. Now, remember, when a substance boils, the water molecules are going to break away from each other and become a gas. Well, if this has a strong surface tension, or the particles are really held close together, all right, it's not easy for this to boil all the time, and sometimes it will go above its boiling point. Now, let's go back to our idea of putting this in the microwave. Let's say that we want to heat water up. This is not a real stable state. And what happens when you boil water, or you put water in the microwave, right? We heat it up and it'll go into this superheating state. And as soon as you take the cup out or jostle it a little bit, all right, it will go back, it will go back to 100 degrees, and all of a sudden, all of this gas will escape explosively. And you get major burns. You get major burns, and this happens. Actually, it happens a lot. People just don't understand, all right, what superheating is, and they don't understand that how dangerous this is. So once a liquid is superheated, when it's above its boiling point, it's not very stable. And all it takes is to shake that liquid a little bit, or if a piece of dust was to fall in here, all right, or something was to fall in there, you put a spoon in there, all right, it would explosively give off this gas, right, and it would burn people. Now, supercooling is the same sort of thing, except on the opposite end, all right, and actually, I don't know if you did the heating and cooling curve lab in your chemistry class last time, but I do a cooling curve lab where we make a cooling curve of water, and it will often supercool. Right, and what that means, and we'll go back to our glass of water again. Right, remember, water freezes at 0 degrees C. Well, if this is pure water and there are no imperfections in here, it will actually sometimes super freeze and go below 0, maybe to -10, but it'll still be in liquid phase. That's called a metastable state. It's not real stable. All right, and if I was to add any type of impurity in here, or to maybe even just shake it a little bit, right, it would immediately freeze. The whole thing, it would immediately freeze. Now, those are just some terms that we need to quick run through. Okay. Now, what I really want to focus on today are our intermolecular forces. The forces of attraction between molecules. Now, if we didn't have intermolecular forces, most substances would be gases. Okay, so these intermolecular forces are very important. All right, and we're going to go through each type of these forces. So let's start with our first one. And this is called a London dispersion force. It's also called an induced dipole force. So these London dispersion forces are the most common intermolecular force. These are found in all molecular compounds. And so we find them in all molecular compounds. Now we see them. We don't see them in all molecular compounds because it turns out that these are the weakest ones. And some molecular compounds have stronger intermolecular forces. So the only time we see the result of London dispersion forces are in the noble gases and non-polar molecules. So these forces allow noble gases and non-polar molecules to be solids and liquids. This is what allows us to have solids and liquids and those noble gases and our non-polar molecules. Like I said earlier, these are the weakest intermolecular forces. So because they have weak intermolecular forces, these are going to have very low melting points and boiling points. All right, now we need to get into what these forces actually are. How do they work? So these are forces of attraction due to what are called instantaneous non-symmetrical electron distributions causing a temporary dipole. Wow, that was a whole bunch. Okay, so these are attractive forces due to what are called instantaneous non-symmetrical electron distributions. All right, well, what the heck does that mean? So let's just, okay, I want to draw some diagrams. So let's just say we have an atom of neon. So remember, neon has 10 electrons. It's got 2 in the first, PeL, 8 in the second. right? So in neon, remember these electrons are in clouds, okay? And they're around this nucleus. So in this case, the electrons are equally distributed around the nucleus. Okay, so there is no dipole here. Remember, dipole means two poles, so one side would be negative, one side would be positive. Right? So the electrons here are equally distributed around each other. But remember, these electrons, okay, they're moving all around here in this random motion. Okay, so the electrons, are moving randomly around the nucleus in the clouds. Well, if they're moving randomly, couldn't we have in a specific instance some more of the electrons on this side than on this side? So for example, let's say that we look at this in an instant of time, and we got 1, 2, 3, 4, 5, 6, 7 electrons over here and only 3 over here. Well, if this is the case, in this instant, this side of the atom would be slightly negative, and this would be slightly positive. Now, would this last very long? No. Okay, it would only last a split second. Right? That's why it's called an instantaneous dipole. It only lasts a split second, right? Because these electrons aren't going to stop. But in that split second, we all of a sudden have a negative end and a positive end. We have a dipole. All right. Well, let's say that we have 2 neon atoms. And in this one, we have an instantaneous dipole where the electrons are all over here, except for a couple. Right? So this side ends up being slightly negative, and this side ends up being slightly positive. At the same time over here, okay, we have an instantaneous dipole. It looks like this. So this side is slightly, oops, that's not what I want. More electrons here and just a couple over here. So this is slightly negative, and this is slightly positive. More electrons. Well, if they're next to each other, then all of a sudden, look here, we have a positive charge and a negative charge near each other. And in that instant, we form an attractive force. And it's only for a split instant. It doesn't last long. All right, and that's what's called a dispersion force. Now, you got to realize that it doesn't happen all the time, okay? But if you think about a sample of neon, we may have moles and moles and moles of atoms, okay? So it's going to happen more often than you would think. Okay? So this is what's called a dispersion force. But there's another thing that can happen with these instantaneous dipoles. So let's talk about that. So the second thing that can happen is an instantaneous dipole can distort the electron cloud of a neighboring atom, causing a dispersion force. So let's see if I can draw this out for you. So let's say that we have some atom and it has an instantaneous dipole. Okay, so we know that it has electrons going on here, and in one instant, all of a sudden, it turns out that all the electrons are over here, and there's only a couple over here. And this side is slightly negative, and this side is slightly positive. And right next to it, we have this atom where the electrons are equal around it. So this is, let's write this over here. This is our instantaneous dipole. And this one is just neutral. But in this instant, okay, this slightly positive charge is attracted to these electrons, and these electrons are attracted to this slightly positive charge. So in this case, the electron cloud is distorted, and the electrons are pulled this way. So all these electrons are pulled over here, which makes this side slightly negative, and it makes this side slightly positive. Now, this is different than the last one that we talked about, because in this one, okay, in the first thing that we talked about, we said, look at this guy and these guys each have instantaneous dipoles. Okay? And because of that, the positive side of this side is attracted to this negative side of this one. This one is different. In this case, we have an atom or a molecule having an instantaneous dipole, and it's causing another atom next to it to produce an instantaneous dipole. And when that happens, we get that dispersion force. We end up with the same type of force. Okay, we still get a dispersion force, but the way it's brought about is different. So let's write this. Electrons are attracted to the positive side of the instantaneous dipole This forms what's called an induced dipole. Okay. So these electrons of this atom are attracted to this instantaneous dipole over here, and it distorts this cloud, and it pulls the electrons over here. And we get this dispersion force. Okay, and it's called an induced dipole because this guy is forcing this one to have this distorted cloud. Now, some atoms are more easily distorted than others, right? And that's called polarizability. 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 Well, this is the tendency for electron clouds to be deformed so that polarity is created. In other words, this right here. The rule of thumb is this. The larger the atom or molecule, the higher the polarizability. Okay, so the bigger the molecular atom, the more apt that this is going to happen. I guess the question becomes why? Why does that happen? Well, it's got to do with the attraction between the nucleus and its electrons. So if we look at small atoms and molecules, in small atoms and molecules, the electrons are held tightly to the nucleus. It's hard to distort the electron clouds. So for example, let's say we have helium. Okay. Helium only has 2 electrons. And they're in that first principal energy level. They're right over in here. They're really close. Okay. There's a very strong attractive force between the nucleus and its electrons. It would be very hard to distort that cloud. That seems to make sense. But what happens in our larger atoms and molecules? Well, in this case, our electron clouds are bigger. The electrons are further from the nucleus. This makes it easier to polarize. I don't know, so let's go to, I don't know, let's say we have like, I don't know, big atom like krypton. It's got, what has it got? 20, 30, I don't have my reference tables with it. 36, I think. It's got lots in other words, it's got lots of electrons, lots and lots and lots of them. And some of them are pretty far out here away from the nucleus. Okay? Way out here in the fourth principal energy level. Okay, so these electrons out here, okay, the attractive force between the nucleus and the electron is a lot less. Right? So this is a lot easier to distort. So in our bigger molecules, we have more induced dipoles. Right? If we have more induced dipoles, that means the intermolecular forces are stronger, which is going to increase our melting and boiling points. Right? So let's go ahead and write this. As molecules get bigger, they are easier to distort the electron clouds and this produces more induced dipoles. Because of this, our dispersion forces are stronger. So that means the larger the molecule, the more induced dipoles we have, dispersion forces are stronger, which means we're going to have increased melting points and boiling points. Now we can actually see this in our group 17 elements. Oops. If we go right down group 7, if we look at group 17, Cl2, Br2, I2. Okay, so these are all diatomics. They're all nonpolars. Okay, so they're all nonpolar molecules. The only intermolecular force between these are our instantaneous dipoles or our dispersion forces. Chlorine, diatomic chlorine, at standard temperature and pressure is a gas. Bromine is a liquid. Iodine is a solid. Right? So the only thing that's happening here is our electron clouds are getting bigger and bigger and bigger and bigger and bigger. Okay? Which means we're getting more induced dipoles, which means we're getting stronger and stronger and stronger intermolecular forces, which is going to increase the melting and boiling points. Right? So as we go down, these clouds get bigger. Okay? They're distorted more often. Okay? It causes stronger intermolecular forces, and it affects their melting and boiling points. That's why we get this difference as we go down group 17. So you need to be able to look at these and determine how strong, or you'd be able to compare the dispersion forces that are being produced. Okay, so remember, the larger the molecule or atom, okay, the more dispersion forces are going to be, okay, which means it's going to give us lower melting and boiling points. Now, let's look at this. So this is our group 17, and then right next to it we have Ar, we have krypton, and we have xenon, group 18. We can compare boiling points this way too. We know as we go top to bottom, my boiling and melting points are going to increase. Our dispersion forces are going to increase. Same thing over here. Okay, krypton has a higher boiling point than argon. Xenon has a higher melting boiling point than krypton. All right, same thing over here. But let's compare this way. Which one of these, okay, do you think the group 17s have higher melting and boiling points or group 18s? Well, you need to think. These guys, this group 17, they're going to have much higher melting and boiling points. Why? Well, my group 18s, these guys, they only have a 1 electron cloud. They're only single atoms. These are monoatomic. Over here, we have 2 electron clouds. Because these are all diatomic. There are more chances to produce this instantaneous dipole over here because there are more clouds. So these guys are going to have much higher boiling points than our noble gases. All right, some other things that we have to consider. Now, I know we haven't talked about organic chemistry yet, and we won't for a little bit, but dispersion forces play a major role in organics. And a lot of our organic compounds are non-polar molecules. So let's go over here. Most of our organic compounds are non-polar. But they can still be solids and liquids. Okay, so they're going to have dispersion forces. And it happens in the hydrogens. Okay, so let's look at CH4. We've got carbon and our 4 hydrogens. We got methane. So this is a nonpolar molecule. And another methane. We can make this a liquid. Okay. So these are nonpolar molecules. The only force of attraction would be dispersion force. And the hydrogens can have instantaneous dipoles. Okay. So this hydrogen can have an instantaneous dipole, and this hydrogen can have an instantaneous dipole, and we can have a dispersion force. Okay. So the hydrogens can have instantaneous dipoles. Okay, so we get this attractive force. Remember, these are non-polar. These are both non-polar. So we get this instantaneous dipole, or this dispersion force, which attracts these molecules. Okay, now remember, this is very weak, all right, but it allows these to become liquids. Now, what if we were to look at, I don't know, butane? Let's say we have 2 molecules of butane. Well, the same thing can happen here. Except this time, look how many hydrogens we have. We could have an instantaneous dipole here and have a dispersion force here. We could have an instantaneous dipole here and have a dispersion force there. We could have an instantaneous dipole here and have a dispersion force here. Same thing here. So the melting and boiling point of this guy is going to be much higher than this guy. And the only difference really, okay, is this is a much bigger molecule, has a lot more hydrogens, right? We can form lots and lots more dispersion forces, right? So the more hydrogens we have, the possibility of instantaneous dipoles increase. So in other words, the larger the organic molecule, the stronger dispersion forces and higher the melting points and boiling points. So now you can compare your organic compounds and you can predict which one's going to have a higher melting and boiling point. I don't know, so let's say we have C2H6, C3H8, C4H10. Okay. Which one of these is going to have the highest melting and boiling point? Well, this guy right here, it's going to have the most instantaneous dipoles, or those instantaneous attractive forces. All right, so this is going to have the strongest dispersion force, which means it's going to have the highest melting, and boiling points. Now, there's one other thing that we need to consider when we're talking about organics. In organic compounds, they can have these side chain things. So let's compare this. We've got butane. So this is butane. It's normal butane. So let's say it's N-butane. And this is C4H10. Well, let's compare it to this. This is still C4H10. They're not the same thing because this is straight chain butane, all the carbons in a row. This one, we have this side chain coming off of it. Right? So this is what this would be 2-methyl propane. Which one of these do you think has a higher melting and boiling point? And why? Does N-butane have a higher melting and boiling point? Or does 2-methylpropane have a higher melting and boiling point? Well, they're both made of C4H10. So you might think, well, maybe they have the same melting and boiling points. But remember, it's got to do with the number of dispersion forces. So as soon as we start adding side chains, these side chains get in the way. So our side chains end up reducing the number of possible instantaneous dipoles. Which means they're going to produce weaker or fewer dispersion forces, which means they're going to have lower melting points and boiling points. Okay, so in this one, okay, if we have these molecules lined up, we already drew this one. Okay, you got all these possible dispersion forces here, but as soon as we have this guy, okay, it gets in the way. Okay, and we can't form as many of those instantaneous dipoles. So this guy is going to have lower melting points and boiling points. This would have higher melting point and boiling points. And yes, you would have to understand that. Okay. Wow, that was all under dispersion forces. We still have some other ones that we have to deal with. They're nowhere near as complicated as this one. So let's run through these. Our second type of intermolecular force is called dipole-dipole. Now remember, a dipole is really just a polar molecule. So a dipole-dipole attractive force is just when two polar molecules are attracted to each other. The positive end of one molecule is attracted to the negative end of a different molecule. All right, so HCl is a polar molecule. This has a much higher electronegativity. So the electrons are pulled towards the chlorine, so this becomes slightly negative, and that becomes slightly positive. Now, if we have two of these molecules, again, the electrons are pulled this way. We have this negative end of this molecule attracting the positive end of this, and we get this intermolecular force called a dipole-dipole attraction. And this is what holds polar molecules together. Now, dipole-dipole attractions are much stronger than dispersion forces. Okay, dispersion forces are really weak. Okay, this dipole attraction that happens between polar molecules is much stronger. So these are going to have much higher boiling points than any of our nonpolars. Now, we can actually calculate this dipole force. right? And it's equal to the negative slight charge times the positive slight charge. So if we know those charges, divided by the distance between them squared. Okay, so the bigger this distance, the closer these are going to be, the stronger the dipole force. So let's just write this. As distance between the molecules decrease, the dipole-dipole forces increase. And so as our distance decreases, our dipole-dipole attraction increases. And then the stronger the dipole forces, the higher the melting point and boiling points. All right. Our third type of intermolecular force is called hydrogen bonding. Okay, and you need to be really careful because hydrogen bonding is misnamed. Okay. It's not a bond. It's not a bond. It's misnamed. So don't think it's a bond. Right? Now, hydrogen bonding is just a special type of dipole-dipole. It's just a special type of dipole-dipole, right? Hydrogen bonding is found between molecules that have a nitrogen-hydrogen bond, an oxygen-hydrogen bond, and a hydrogen-fluorine bond. Okay, so if we have this type of bond in the molecule, okay, we're going to have what are called hydrogen bonding. Now, what is hydrogen bonding? In these three bonds, there is a large electronegativity difference. Between hydrogen and the nitrogen, oxygen, fluorine atoms. This makes for a very strong dipole-dipole force. So let me see if I can give you let me see if I can clear this up for you. Hydrogen bonding and dipole-dipole forces are the same exact type of force. So when the positive end of one molecule is attracted to the negative end of a different molecule. Okay? The only difference is in these ones, okay, the opposite ends are just much more negative or much more positive. Okay, and because of that, you get a much stronger force of attraction. So if we go back to our HCl, the electrons are pulled this way, and we get this slight negative and this slight positive. Okay, and we get this attractive force between them, which is called dipole-dipole. Okay, the negative end is attracted to the positive end. Well, let's compare that to what happens in HF. Well, in this case, fluorine is 4.0. This difference is very big. The electrons are pulled way over here towards fluorine. Way over here. So in this molecule, the fluorines are very negative, and the hydrogens are very positive. This positive is still attracted to this negative, so we get this force, but the force is much stronger because of this bigger negative and positive charge. This is what's called a hydrogen bond. It's not a bond, right? It's a force of attraction between molecules, all right? And it's the same thing as a dipole-dipole, just much stronger. So now, in regular chem, when we taught these forces, we said it only happened between three molecules. So we said, look at hydrogen bonding is going to occur between ammonia, hydrogen fluoride, and water. Okay, so these are our molecules with hydrogen bonding. And because of that, these have abnormally high melting points and boiling points. Now, when we look at these, this has the lowest melting points and boiling points, and water has the highest melting points and boiling points. And we need to understand why. Well, ammonia and hydrogen fluoride tend to form chain-like structures linked by hydrogen bonds. So for example, HF, 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 HF. Right? And then we get these hydrogen bonds between them. Ammonia does this. It forms hydrogen bond here, a hydrogen bond here. So these are our hydrogen bonds. Okay, so we get these chain-like structures. Okay, and we could have more coming down here. Now, this has a bigger charge difference, so this hydrogen bond ends up being a little bit stronger than this hydrogen bond. Right? So why does water have the highest? Well, that's pretty cool. Water's different. The electrons are pulled up here, and this becomes very, very, very negative. This hydrogen over here becomes very, very, very positive, and this hydrogen over here becomes very, very, very positive. It will make 2 hydrogen bonds. Okay. Ammonia won't do that. Okay. It'll only make 1 hydrogen bond. Okay. Hydrogen fluoride will only make 1. Water will make 2. So this gives, this gives water the highest melting points and boiling points of the 3. So what does it look like? Well, we can end up getting structures like this. So it's forming those 2 here, okay? So we get all these dispersion forces. Okay, these dotted lines are dispersion forces. Okay, so this is going to have higher melting and boiling points. Now, are there other molecules that have these OH bonds, NH bonds, and HF bonds? And the answer is yes. And most of the time, we're just going to be looking at the NH and the OH bonds. So molecules with NH and OH bonds will produce hydrogen bonding. So for example, our organic alcohols. This is methanol. In methanol, we have this OH bond again. Okay. The electrons are pulled way up here, so this becomes very, very negative, and this side becomes very, very positive. We can form hydrogen bonding between these molecules. As soon as you see this OH, okay, hydrogen bonding is going to happen between those types of molecules. Okay. Amines and amides will happen too. So let's say that we have something like this. In this case, we have that NH bond. So my electrons are going to be pulled towards nitrogen. Okay, this is going to be positive, right? So this is going to produce hydrogen bonding. Organic acids. It's that COOH group, COOH. And I know we haven't talked about organics yet, but it looks like this. Here it is again, right here. Slightly very negative, very positive. It's going to form, hydrogen bonding. Okay, so if your molecules have this OH or this NH bond, it's probably going to form hydrogen bonding, and these are going to have higher melting and boiling points. Now, you need to be able to look at a molecule and decide what you have to be able to rank them by melting and boiling points. Right? And I just want to show you this. I'm going to post this for you. This is a way to come up with the type of intermolecular force. Okay, so you just look at it and you say, hey, are there any ions present? Okay, if we have ions, are they polar molecules? Yes or no? All right, and you get these different types of forces. Right, so this could help you come up with what type of forces they are, and that tells you what type of strength they have also. Right, so these are dispersion forces, dipole-dipole, dispersion, dipole-dipole, hydrogen bonding. We're going to talk about this next class, and then we have ionic bonding. Okay, so it helps you figure out what type of bond or what type of forces there are between these. Right, so this is just something you can use. Okay. And I will post that. So, predict the type of intermolecular force and rank in order of increasing boiling point. C6H6, CH3OH, C5H11OH, Cl2, CF4, SO3, xenon, C2H5NH2, XEF6, and HBr. So let's just look at these real quick. So you need to be able to look at those and say, hey, what type of intermolecular forces are we going to have here? And there's a lot involved with that. I get it, but we should be able to do it. All right, so let's look at these first. C6H6. All right, so this is an organic compound. Most organic compounds are nonpolar, right? And this is an example of a nonpolar compound, okay, which means it can only have dispersion forces. This is another organic compound, but look here. It's got that OH on here. All right, so this is going to have hydrogen bonding. Here's another one. It's an organic compound, but it has this OH. It's going to be hydrogen bonding. Diatomic chlorine, non-polar molecule, which means it's got to be dispersion. CF4. Tetrahedral, all the same. This is a nonpolar molecule, which means it has to be dispersion. SO3. This is trigonal planar, which means it's a nonpolar molecule, which means we have to have dispersion. Xenon. It's a noble gas. Nonpolar, it's got to have dispersion. An organic compound, but it's got this nitrogen-hydrogen bond. This would be hydrogen bonding. XEF6, an octahedral. It's nonpolar. It would have to have dispersion forces. HBr. This is a polar molecule. Okay. It would have dipole-dipole. Right. So you should be able to look at each one of these and tell me what type of intermolecular force they have. Now we can go back and we can rank them. Which of these is going to have our highest boiling point? Well, it's going to be one with the hydrogen bondings. Okay. So the question is, which one probably is going to have the highest boiling point? Well, we know that this OH bond is stronger than this NH bond. So these guys are going to have higher boiling points than that one. So then the question becomes, which one do you think of these has the higher boiling point? Well, remember, these also have dispersion forces also. This one has more dispersion forces, and it has hydrogen bonding. So this one would probably be the highest, if we were to guess. That would be second. This would be third. Right, so there's our hydrogen bondings. What's next? Okay, well, our dipole would be next. That would be 4. Then all of these other ones are dispersion forces. And we would have to look at electron clouds, and we would have to look at masses and that kind of stuff. All right. So, that would take some time. Right. We do know some things. We're not going to go there. So we could look at these masses and we could figure out which ones are have the strongest dispersion forces and which ones have weaker ones. All right. But we're not going to go there for today. All right. But you need to be able to look at these different dispersion forces. All right. That's where we're going to end for today. I know it was long, and we will pick up with intermolecular forces next class.